So on the pictures below, I have added Sally, Sally the squirrel, which is either helping or hurting Max. So again, if I represent the forces here, and so here Sally is not helping Max, so I would label my forces this way. Again, I have the force of gravity acting downwards. I have a normal force opposing gravity, equal and opposite. They will cancel out. Max is pushing in this direction with 48 newtons. But Sally is pushing in the opposite direction with 12 newtons. So if we take a look at the force diagram, I see that the forces in the y direction are in equilibrium. The normal force and the gravity will cancel out. This box is not going to accelerate up or down as long as the floor holds out. So that means the net force in the y direction is 0. When I add up all the forces in the vertical forces, they cancel each other out. However, the forces in the x direction are not 0. So a word of caution. Often when they write a vector equation, they won't indicate the direction, that is the signs, right away. So in this case, I like to keep a vector hat on my variables. So I could write what's happening in the x direction, that this is going to be equal to the force of Max plus the force of Sally. Now, it's not a fast rule, but when I personally write my vector equations, I try to keep the vector hat on my variables until I account for signs. But I can see that Sally's force is in the negative direction. So this is really going to become, if I take away those arrows, a positive force for Max, but minus Sally's negative force. Or another way of saying, Max is pushing to the right, Sally is opposing that by pushing to the left. And then, because these forces are not balanced, these would be equal to mass times the acceleration in the x direction. Or that the acceleration in the x direction is going to be equal to, well, Max's force is 48 newtons. If I subtract Sally's force of 12 and then divide by the number of kilograms, well, then I would have that 48 minus 12 is 36. 36 divided by 12 is going to be, this is going to be an acceleration of 3 meters per second squared. It's positive because the acceleration is going to be going to the right again, just not as much as before. Well, instead of opposing Max and Sally's helping out Max here. And so again, the force diagram would look something like this. I would have the force of gravity, which is equal to 120 newtons. Again, that equals to mass times gravity. I'm using gravity. The approximate value of gravity equals 10. The normal force here, and I should say that this is minus 120 newtons down. The normal force is going to be equal to plus 120 newtons. Now, since Max and Sally are both pushing in the same direction, I would have 2 arrows pointing to the right. Here is the force of Max. Here is the force of Sally. And I would say that now force Max plus force Sally equals ma in the x direction, or this would be 48 newtons plus 12 newtons equals 12 kilograms times ax. 12 and 48 is going to make 60. 60 divided by 12 is now going to give me an acceleration of 5 meters per second squared in the positive direction. There you go. All right, so again, it is perfectly okay in most problems to put the forces on the picture. However, it is very common in AP problems or in some textbooks that they ask you to make a separate force diagram. And again, we call these force diagrams a free body diagram. It's simply a diagram showing the forces acting on the object. One more example before we wrap this video up. Okay, so we have the same crate, but now being pulled by our friend Debbie, the circus bear, who is pulling the crate with a rope. Now, a quick reminder of the forces that we've discussed. We've been talking about weight, which is also the force of gravity acting on an object. Then we've been talking about the force, the push from the floor or the ground. That's known as the normal force. So your weight is between you, is the pull of the earth acting on you. The normal force is the push from the ground. Or more generally, the push from a surface. We are also in this picture going to have a tension. Typically, we'd label that FT. In this case, I'm going to label it FD because it's Debbie's tension. But a tension is the force along a rope or a string. Now, so if I look at the forces, now the odd thing about tension is tension exists everywhere on the string. So as Debbie pulls the box, the string is also pulling against Debbie. Now, that's why it's important to note which object we're looking at. So we are interested in the motion of the crate. So I'm not going to be concerned about the force acting on Debbie. So although that force is there, I'm not going to put it on my diagram. I'm only going to diagram the forces acting on the crate. So as before, the force of gravity will always be pointing down. The normal force is always perpendicular to the surface, which in this case is equal to, is vertical. But now Debbie's force is going to be applied along this rope. It's a tension. Now, I say here that I have a force at an angle, and you can pretty much guess what's going to happen. We're going to need to break these up into X and Y pieces. However, before we do that, there's an important thing to note about the AP exam. On the AP exam, when they ask you to create a force diagram, they insist that it only shows the actual forces. That is, not the pieces of the force or a component list. So whenever you're diagramming forces on an AP exam, you never put components on your force diagram. This would be the correct force diagram for this problem. Now, it's correct, but it's not as useful to us. And remember, this is what's known as a free body diagram. Okay, do not put components on your diagram. they will mark it incorrect. Now, all right, so it's perfectly okay, though, to make a second diagram with your component, so let's do that. So Debbie's force here, which is equal to 150 newtons, is at a 40-degree angle with the horizontal. Now, when we break our vectors up into components, like we did with displacement and velocity vectors in the last unit, I can label this as the x part of the Debbie's force. Now, it's important to recognize that the y part is actually over here. That is, if I imagine that Debbie's force was made out of two separate pulls, one vertical and one horizontal, they'd be pulling at the same starting location right there. But we typically rewrite that y component over here so we can see how it completes our triangle. And that's okay. Just remember that when we do our diagram, it's really acting on this point. That works out to be 115 newtons. And for the y, that's going to be 150 newtons times the sine (150 newtons times the sine of 40 degrees). So F dy is going to be equal to 96.4 newtons. If I keep it in 3 sig figs, we might as well. So let's make this 96.4 newtons. All right, so now if I do a force diagram with the components, the picture will look a little bit different. So now with the individual components, well, I still have the weight vector, or gravity. And remember, that's 120 newtons in the down direction if I assume that gravity is 10. Now, let's talk. I have Debbie's forces acting on it, but now I want to put in the components. So if I'm doing it to scale, this Debbie's x force is just slightly smaller than the weight. So it should just be a little bit less. So this is the x part of Debbie's force, 115 newtons. Now let's add the y part of her force. That's 96.4 newtons. And here's our first observation about the normal force. When students first start working on physics problems, they often assume that the normal force is the same as the weight. But that's only true if the normal force and the weight are the only two vertical forces. Now remember, this is not a math problem, it's a physics problem. Now think logically what's happening. If you start pulling upwards on a rope like Debbie's doing, the ground does not have to do as much effort in order to counteract the weight. That is, there are now two forces in the y direction helping to support the crate, both the normal force from the ground and Debbie's y component. So if Debbie, together these two forces are going to have to add up to the weight of the box. So the normal force now is actually going to be much smaller. This is almost 100 newtons by itself, so the normal force is actually going to look more like this. So the first thing to note is the normal force depends on the situation. So the size of the normal force really does actually depend on what else is going on in the problem. So up here, technically in our original diagram, that normal force is not drawn to correct scale. Now, until I actually look at the components, I would not necessarily note that. So be careful. Usually on an AP test, they would let you know when your arrows must be drawn to scale. We try to do it anyways, but sometimes if we're not thinking all the way through the problem, we won't get the links correct. So the normal force depends on what is happening. Since I know the crate is not accelerating in the y direction, I know all my y forces must cancel out. So when I look at this logically, together these two forces must be equal to 120. So let's take a look at what that means in our force diagrams. So in the y direction, the sum of the forces in the y direction are equal to 0. Now that's an observation because the crate's not moving up and down off the ground. But there are now several different forces acting on it. I have the normal force, which is a positive force, plus I have the y component of Debbie's force, and then I have the force of gravity in the negative direction, and together these add up to 0. Now notice I didn't put vector hats on the F's because I've already put in the signs. Now also notice that I know the force of Debbie and I know the force of gravity, so I can actually find this normal force if I need to, which I don't in this case. In the x direction, there is only one force in the x direction. That force in the x direction is equal to the x part of Debbie's force, and that would be equal to the mass times the acceleration in the x direction. So if I needed to want the acceleration acting on this crate, I would say that the acceleration was equal to Debbie's force in the x direction, the x component divided by the mass. That's going to be equal to 115 newtons divided by 12 kilograms. Positive. All right, one last observation. Debbie's a big girl. She's a bear on a bike. She can pull a lot harder than 150 newtons. What would happen if Betty pulled so hard that the y component of her force was larger than the weight of the box? That is, what would happen if Fdy was greater than 120 newtons? Well, in that case, our observation about the acceleration being 0 in the vertical direction would be incorrect. If Betty pulled so hard on this force that the y component of her force was larger than the weight, the crate would actually lift off the ground. And at that point, you would have no normal force. So an interesting observation is the point of which the box would actually be lifted up is when this normal force becomes so small that it becomes 0.